glad to be here. I wish I could meet you all in person, but sadly the circumstances are a bit different this time. But I still hope you'll appreciate this talk and learn some things. Also, thanks to Luca and Comstack for having me here. And let's go. So today I'm going to be talking about basically three things. The standard ways of inspecting live systems in production, inspecting distributed systems in production, and also some hacks that we will use to make it all work in a functional ecosystem. So let's go through a case study. We are going to be processing payments, and yeah, basically each payment will have an ID. We'll get it from somewhere. I assume it will be an HTTP request or a message. Doesn't really matter. We'll get a payment ID, and we need to add some information to this so that if there are any problems with this code, we will be able to understand what's going on in production. So the standard approach would probably be to log some things. So I'm going to log the payment ID before I start, and then I'm going to log the result of this whole processing thing. Note that I'm not repeating the ID of the payment because, well, I don't need to. It's already there in the first message. So if we look at the logs, we can see all the results of all the payments that we've made. There's just one problem with it. We don't see which result comes from which payment. So how do we solve this problem? Well, one approach that you might think of using is logging the thread that we are logging on. So in a single threaded processing, we will see that the thread is the same when we start and when we finish. So we can still grep for this and see which result came from which payment. So great success, right? We can go home. Well, is it really? Because there's one big problem with this. When we see a message, how do we know that it's from the same request? Because threads may be reused between requests, between sessions, between transactions and users. So that's just one problem with this. So can we solve this? We can, of course, log the payment ID in every message, just like that, and then grep for that. But it's not going to be fun. I swear. You are going to make mistakes. You're going to use different formats for logging this, and it's going to break. We can use something like structured logging. So this would have some sort of this payment ID would be part of the metadata, not just the text, but it still sort of has many problems. So one approach to doing this kind of structured logging that also is based on some context is using the mapping diagnostic context or MDC. It's part of SLF4J, logging facade for Java and the JVM applications. It has a relatively simple API, which can be roughly translated to Scala like this. We have a method to put some value under a key. We have a method to remove a key, to clear the whole map and get a copy of the map that is underneath. And we can also put a key using closable, which will, when we close this, will be removed. So this sounds exactly like something we might want to use. So if we set the request ID, or something that's more generic than payment ID, if we set it before our processing, and then we remove it after the processing, we should be able to see each transaction with a different ID. And then we can actually grep for a transaction or a request ID, and we'll see only things from that request. There's no way of mixing this up with a different transaction or okay, questions, no questions. Okay, it's not going to be a different transaction, and we will basically, when we see the last message with the same request ID, that's the end of the request. Okay, so that now it's at least explicit where the request ends. But what if the thread changes? Does MDC still work in that case? Well, it turns out it doesn't. And this is a huge problem because right now I don't think anybody builds applications in Scala that execute a single request on a single thread. And if you do, well, I guess it might work for you, but it won't work for me. So why did this happen? And to understand this, it might be worth to look at how we do async programming on the JVM. Basically, what we do is when you have a synchronous request, you have a series of statements that you run one after the other. But with asynchronous processing, you will actually sort of schedule callbacks. So you will do one thing, and when it's done, you expect the runtime or whatever library is actually doing the async stuff. You expect it to call this callback with some result. So in this case, we will have one thing, then in that callback, we will start another thing, and in its callback, we will do more things. And in Scala, we have a pretty standard way of doing that based on monads or monadic combinators like flatmap and map. And even Future provides something like this. So this is basically the same kind of structure, except we have special syntax for it that makes the nesting less painful. So the nesting is now hidden, and we have the same thing as a structure, a piece of code that's similarly structured to how we would do standard synchronous imperative programming. We just have this for around it. So this is pretty nice, but how does it work, and how can we make it work with our MDC and stuff like that? Well, when we do map or flat map on Future, any kind of combinator, it usually takes an implicit execution context. And what that means is that it takes a sort of representation of a thread pool or something like that. There doesn't need to be any pool underneath, for example, in Scala.js. But there's usually a thread pool in this execution context. And when you map to an execution context, that basically means that this piece of code will run on one of the threads from that execution context. So basically, we start on the main thread because we have a successful feature, or whatever thread called this piece of code. And then we submit to the first execution context to run this f of 42. Then, with the result of that, we will run another function on the other execution context. Of course, this might be still the same execution context. And if it is in Scala 213, for example, it might be actually the same thread, which is pretty cool for performance. But in theory, it could be a completely different thread from a completely different thread pool. So basically, it will look like this. We will just execute some code on the first execution context, and then when the code is done, we will execute some more code on the other context. So where is the context lost? Well, the context is lost between the call to execute and the time that we actually evaluate this runnable that we passed to execute. So one thing that we need to do is the best approach to this, and the simplest one, is to sort of catch the context before we go into execute and then inject it into the runnable. And we can do this. We will use something like run with context, basically a function that takes a context that we want to run some code with. It also takes a chunk of code and basically gets the context before, sets the context to the new context, runs the block of code, and then restores the old context. So this will work for anything, for MDC, for anything that does this kind of thing based on thread locals and so on. Actually, I forgot to mention, MDC doesn't, this asynchronous thing didn't work with MDC because this map in MDC is stored in a thread local, so it won't automatically propagate between threads. So, but we can make it propagate if we wrap around our execution context. So if we think of an execution context as a function from runnable to unit, which it pretty much is, then we can take one execution context and add some superpowers to it. So there's one question: is using your code? It's not. It's in Scala 213. It's standard code. It's sort of like resource or try with resources. It's pretty cool, but of course mostly for impure code. So back to this. So given these two functions, well, methods, one for getting the current context on the current thread, and one for setting the context, we can build something like a wrapper of an execution context that returns another execution context, which does what I said we would do. Get the context before submission, then submit, and inside the runnable, run the original runnable with the context. And surprising as it may be, it works. So now the code on the left is what we had before. The code on the right is what we will have now. So now we have this new context, this context that we don't want, the blue part, just for a while. It doesn't ever reach the code that we actually want to run on this execution context. So then we set the context that we had from the original thread, run the code that is supposed to run, and then restore the context. So yeah, here's a more graphical representation of this. If you want to look at how maybe this is more clear to you. But basically, we get the context, we schedule something to run on a different one, on a different execution context. We restore that, run the code, and restore the context that was originally on that thread. So that when we are done with this and we switch to another thread, the one that we did the work on, the EC1, has whatever it had before we went to it, which will usually be the main context, but you get the idea, the root context. So if we wrap an execution context and we use that, well, suddenly everything works again. So we can now also grab for the request ID, and we'll see everything from this transaction in there. Okay, so does it work with functional code? Does it work with I/O? And if you instrument your context shift, which is probably the most important piece of machinery that you will use when changing threads in classified I/O, it might work, but well, it doesn't really. It's not enough. And the reason why it's not enough, maybe you can figure it out. I'll just give you a couple seconds. Maybe there are some suggestions. Okay, so nobody has an idea, but it's basically lazy evaluation. So when we set the context using this using resource or put closable, we set it on the thread that only creates the data structure, the I/O, but we don't start this I/O in this block. So when we've created this I/O, we've returned it from the using resource block. Then the resource is closed, and only then afterwards, maybe someone will actually execute this I/O. So by then, the context will be long gone, and we will never see it again. So we need to adapt this piece of code, this old run with context, so that it works with I/O. And it's not really that hard. Like we just need to lift the get and set to I/O. And instead of try finally, we will use bracket. If you want to learn more about what bracket is, it's basically try finally, sort of, for the functional folks. And it's pretty well documented in Classify. So if you're not familiar with it, just take my word for granted and then go to the docs to find out more. But now we have these two functions, well, this one value and one function that we need to implement. So the get is pretty obvious. We just get the context from the current thread, that the same way as we did before. We just lift it to I/O. But then there's the set. And this part is, well, I'm having trouble with it. We have one way to do it by just lifting the set as before, but it may not always work. It'll work for MDC because we have this kind of function like set context map. but it might not work for other things that we will see later in this talk. Okay. So how would this work if we use set context? Remember, we have this bracket inside this with context. So first, we will get the context. Like this is the first part, just get context, right? We will get the context, set the context of the current thread to the new one, the one that we passed, this new context. Then we will run FA, so launch some missiles on the same thread, and then restore the context. So pretty much what we had in run with context. But if we have something more complex inside FA, for example, if we change threads, so in this case, I will just shift execution to the execution context, which basically means it might change. If we are already on this execution context, we will submit a task to it again, so that maybe it runs on the same thread, maybe not, maybe a different one. But if we are on a different execution context, then it will definitely change threads. So here, keep in mind that we are still using the instrumented execution context. So the first like get context, set context parts, they come from this bracket, but when we shift, that will also like take the context before. I think that's not on this diagram, but yeah. Anyway, but what is happening is before each of these synchronous blocks, so there's pretty much nothing in the shift that's synchronous, but then we have this launch missiles. All of that is wrapped in this series of getting and setting the context. And all the threads that are working here have the same context before and after they do this FA. So that's really important to just keep the context clean as it was before. And there's also another hack that we can use. So this one is more suited to APIs that don't really provide set and get. Sometimes we just have run with context. So a way to set the context in a block of code and then run the block of code aside. So here we are using a trick with IO async, and to understand how this works, we'll need to dive a bit deeper into IO. And yeah, this will work for APIs that don't provide set context. So a quick introduction to IO async for those who are not familiar with that. IO async has this kind of shape. So it takes a function that takes a callback, right? So this is the CB part that we had. It's a function from either of throwable and A to unit. And basically what that is, this is the rest of your program. So when you run something when you use IO async and you get this callback and you run that inside, for example, from a scheduled action, this will trigger the execution of the rest of your program. Of course, it's also wrapped in some cool things so that, for example, running it twice doesn't result in running the whole program twice, but that's just a detail that's not really relevant here. But basically, we have this program in which we sleep, and the sleep is an IO async node, and then we flat map to something that does some more IO. We can think of this. We can think of this callback as just sending the missiles. So the whole program, the whole prog thing, is basically scheduling the sending of missiles, right? So when we use IO async to set the context, we basically say run the rest of the program with this context until we change the thread. Because I actually forgot to mention it here. This callback is basically whatever is next in this IO until we have another IO async. All right. It's not really like precise definition. If you want to learn more about how this is implemented and how this works, you can check out the talk linked below by Fabio. It'll give you a nice overview of how pipers are implemented and why this has to work like that. Right. So when we actually use this implementation of set context, we will have a lot more nesting in the context scoping thing. And if you look at the diagram, it will become much harder to decipher. But you can still see that the thread, when it's done with its work, it has the same context as before. So we are all good. And when we do some async inside the FA, we will still have the same kind of guarantee that each thread begins execution on the same thread, with the same context as it ends. Okay. And there's just one more trick that we need to do to get this to work. We need to shift before the async. And why is that? This is actually pretty interesting, and I spent a moment trying to understand why it happens. But basically, I/O will not always immediately run the rest of the program in the CP. If we do something like this, we have two subsequent async nodes in the program, then you would expect that the first one, the first before, will be the first thing you see. Then you'll see before the second, like CB2. Then you'll see the foo, the last node in the program. Then you'll see after CB2, after CB1, but that's not what happens. So CB2 is pretty much immediate. It doesn't do anything, you might think. But the reason why this happens is that if you are not the first async node after an asynchronous boundary, then your callback will actually not be the rest of the program, but this will be putting a runnable on a queue. So when this is basically a measure of stack safety in IO async, and it's not really relevant to the topic of this talk, but it's really worth knowing that this happens. So if we shift before, then we are the first node after the async boundary, and then we can safely run the callback and expect it to be the rest of the program before an asynchronous boundary. Okay. So actually, I'm not sure about that asynchronous boundary stuff here. I'll have to get back to this. Okay. So which solution should we use? And noise. Yeah. So these things are really hacky, and I'm aware that this is really complex for such a simple thing that we want to do. But I would still go with the first hack because it's just so much simpler, and this is pretty much the simplest thing that you can do. So until I figure out that this is wrong and doesn't work, I would recommend that. So if you're looking at me like this right now, then you're not alone. This is hard. This is insanely hard. And I understand it may take a while to process. And as you can see, I'm not even completely sure that this works as I would like it to work. So if you have any thoughts about the complexity of this, you're not alone, okay? So we will be looking for a different solution. But for now, can we go with this? We have instrumented our execution context. We have wrapped our IOs in ways that allow scoping in a request ID. Is it going to work? Well, I don't know about you folks, but every month I spend a week on PagerDuty. So at 3 a.m., sometimes, or at any different point during the day, I might get a call, or I might be woken up with lights and memes. So then I usually ask this kind of question if I see a problem with an application. Well, if someone calls me with a problem. Who called this application? Why? What applications did my application call, and which URLs did it try to access that maybe one of them failed? What were the response times? Maybe something took too long and it's beyond my control, or maybe it is in my control. And I want to know that so that I can look for the root cause much more easily. And how long did the whole take? That's like the next step. And were there any errors? That's also what you want to know. This should be pretty much the first thing. So logs don't give us all that information. If we log in a processing pipeline, or whatever you call it, we have a linear structure of events. this is pretty much just events. We have timestamps with some information on them. We don't have any kind of hierarchy. We don't have we don't have a notion of duration. So when did this start? When did it end? We can add that if we add some more logs, but then we need to manually look at that and find the logs that correspond to each other, and then subtract how long that takes. And it's not going to be fun. It's not going to be fun at 3 a.m. and it's not going to be quick. So what if we had something more structured, something more hierarchical, in which we have a transaction as a sort of single chunk of time, a period of time, that is also divided into smaller pieces, smaller periods of time, that correspond to pieces of your program. So in this way, we would immediately see what order the actions were. We can see which things were executed in parallel or concurrent to each other. And we also see how much each of these parts takes. And then if we click on one of these, we can see some more details so that we are not shocked by seeing all of the information at once. We just see the minimal useful thing, and then we can expand later. And yeah, I think this is pretty, this would be pretty nice to have. So of course, this is distributed tracing, which is, this is a really nice definition that I just saw a couple of days ago on a blog post. It's a form of structured logging that assumes duration and hierarchy. So this is a screenshot from Honeycomb. This is it's one of the implementations of distributed logging, distributed tracing, systems for looking at distributed tracing data. And basically we have a trace, which is a single transaction that may be one or more services. And then we have spans in it. So each span is like the period of time. And the span can have children, a span can have parents, but there's usually, well, this should be this root span, which is the thing that actually originated the transaction. Okay, and there are many solutions for doing that, to display the traces and to manipulate them. Honeycomb, Zipkin, which we'll be looking at in this presentation. There's a couple more. Some of these are open source, some of them are proprietary, but all of them are very useful. And if you want to do something like that, I recommend you check out which one suits your needs best. So we'll have another case study, which is a bit different than what we had in the beginning. But basically, what we want to do, we want to make an asynchronous call to a database, which will be simulated by a sleep here because I just didn't want to dive into database territory in this talk. We'll have an asynchronous call to another service, a remote service. We will use an HTTP first client. And then we want to log before and afterwards. And we want to see the span and trace ID in each log. So maybe this isn't clear, but a trace has an ID, and each of the spans needs to reference this trace by that ID. And each span also has an ID and possibly a parent ID. So this, if we put this kind of information in the spans, then the system like Honeycomb or Zipkin can combine that into this view that you can see on the screen. So our reference implementation doesn't do any tracing at all. It doesn't do any MDC explicitly at all. We just have some parameters to a function that are not trace related. This is just like domain data. Let's look at how it would work. First of all, we will create our own model of a span so that we are not tied to any implementation like Zipkin or Jaeger or whatever. And in the first approach, we will keep track of the context of the span and trace by passing parameters around, just passing parameters to functions. And we will need to propagate that information to MDC, to the logger, and to the remote service. So the usual approach to propagation of this through HTTP is to insert the span and trace ID into the headers so that the service upstream can take that and use it as their own span. And you would do the same thing for asynchronous communication through Kafka or whatever broker you use. And at the end, when we are done processing in our code, we will convert to the model of Zipkin, because that's what I decided to use in this talk, and then report each span as we go. So the model may look like this. We'll have a name. This is what will appear in the main view. You'll see the names and the durations. We'll have a trace ID, of course, because as I said, each span needs to have a parent trace. And each span has an ID and possibly a parent span ID. And you can also add some tags or extra values to it, such as the response code of an HTTP call, or maybe the exit case of an IO, and so on. We can also, actually a common approach is to also insert the DB query if you're in a DB transaction. So this kind of thing that is not really that sensitive, you would put into the span tags. So in the no magic approach, where we pass parameters around, we would have to use some, well, we will just have to do that. Like we have a root span that we will pass to the function that does the database call. We will create a child span in that root span. We will set the parameters. This is going to be manual every time, unless we have some specialized instrumentation for like JDBC or something like that. But if we want to add any custom tags, we'll have to do it that way. And then we get a new span, the child span. We provide it to the logger so that it sets MDC. This is included in log4cats. And then we do the sleep. And we do the same for the client, except instead of the logger, we will provide the child span we will convert it to headers and put that into the request headers. All right, and now our main logic function looks like this. We just forward to these two functions and do the logging. Again, we supply the span to the logger as a map so that it gets put into MDC. Okay, and then we can see something like this in Zipkin. This is going to look the same in every implementation that we have in this talk. But basically, we have this kind of hierarchy. It works. We have one span at the bottom that was actually reported by the upstream service. So because it was the same trace ID, and in fact, it was the same span ID, it had the parent span the same as the remote call. It was basically displayed in the same trace as a child of the client call. And you can see actually that the DB call span is highlighted, and we can see the tag, the DB query that I inserted right here. So that's also pretty cool. And if we look at the logs in Kibana or any other logging display, logging dashboard, we can see we are able to insert the trace and span IDs using MDC. If you want to look at the details of how this is passed, I also invite you to look at the source code of the talk. So there's another approach that we can use, which is fairly popular, especially if you are coming from a Play or Akka environment, which is Common. So Common is basically a toolkit that includes a couple of libraries. They have their own instrumentation library, but basically an agent. And they also provide an application metrics platform that you can buy. But you don't need to use that. You can just use Common to report traces and metrics to any of these, like Zipkin or any other commonly used tracing platform. So we will use it here it also provides the means to just to carry the context around, and it still uses the thread local magic or thread local machinery as MDC. So here we don't need to pass any parameters around. We just need to do some hacks. So basically we need to instrument the execution context in a pretty similar fashion to what we did with MDC. We need to instrument to create this sort of with context for I/O. So this is used underneath in child span that you can see in the client and DB calls. But then it is mostly going to work. And there's just one more catch, that sometimes we run something that doesn't really keep the context and we have no control of that. For example, in Blaze, the HTTP first client, I noticed that I wasn't able to keep the context like automatically. I wasn't able to instrument the client to do this. But then you can wrap each such call, be it Blaze, HTTP first, or maybe Elasticsearch, another use case that I had to wrap this thing. We are able to sort of manually catch the context before, then run the action, and then set the context again, which is sometimes fine, sometimes not. But in this case, it was okay. So just to sum up these two approaches, in the direct parameter passing approach, we had quite a lot of boilerplate. It changed all our code because if you have some sort of dependencies, you have multiple algebras that talk to each other, and you have like 3 levels of algebras. Each of them, each single one of them will need to be aware of tracing and of the exact model that you will use to pass parameters. Otherwise, you will not be able to pass the context downstream, and that won't really be nice. You need some extra work to integrate with MDC. This is just passing a parameter, but you need to remember about that. And then to report these traces, you need to do it manually. There's no runtime system that will catch all the traces that you create, all the spans, and report them to Zipkin or whatever. But on the upside, there's no magic, there's no reflection, no instrumentation through aspects, no thread locals, unless you're using MDC in some parts. But it's not all managed by magic. It's managed by you in your code. So that's kind of good. And there's not really a lot of room for context. So there's one question. Yeah, you cannot. This is inevitable, but this is not the end of the talk, okay? We are getting there. We still have some time, and we are getting to the cool stuff. So we can see good things on both sides here. Common, maybe it's not really nice because it has a lot of magic like AOP, so aspects, and thread local based implementation of context passing. There's the instrumentation for async IO. I think it's very complex and pretty fragile because you can lose context anytime you encounter a new kind of asynchronous interface. So that's kind of the next point. Each asynchronous interface, whatever style of callbacks you use, you might have to instrument it manually. You could do this with an aspect, but for certain reasons, I don't want to do that. But on the upside, we have no changes in APIs, so it doesn't pollute all the calls. We have pretty much no boilerplate for passing the context around. We have many integrations, like really. We have integrations for logbacks, so automatically passed to MDC. The trace and span ID are passed to MDC automatically. We have Zipkin, we have Jaeger, we have JDBC, we have Akka, Play, HTTP4S. Many libraries or tools are integrated, common integrates with. So there's a lot of prior art here, and it would be foolish to just throw that away if we can use it. So both of these solutions have shortcomings, but they also have some good parts. So ideally, we could combine all the good parts of that, including no boilerplate, no magic, no virality. What I mean by that is that the APIs are no longer polluted with the span information, the tracing information. We just focus on the business logic as we would like to, and the spans are managed in some different way. And we would also like to have lots of integrations so that we don't need to write them all ourselves, so that we can use like Zipkin right away with just a single dependency and maybe 2 lines of code in the whole application. And MDC is also really nice when you, for example, when I get a call on an incident, the first thing I look at in case of errors is logs. So I want to see the trace ID there so that I can take it, go to Zipkin or some other system like that, and search for this trace and see the whole tree of all the calls that were part of that trace. So all the applications, maybe it's 10 applications, maybe it's 2, but it's still very useful to see. And ideally, I wouldn't like to report every span or every trace manually, because I am going to forget doing that. So in a perfect world, something would manage that for me. So what would it look like? If you write something like Tacos Final, you will have programs that take a bunch of constraints on you, in fact. So one of these could be a trace constraint. And using that constraint, you would be able to maybe wrap a block of code, an f of a, and name it, and that would be a new span in the current span. And ideally, you wouldn't even see the current span because you wouldn't need to. Like, it should be obvious from this code that this execute span or the summary span needs to be created as a child of whatever span you're in right now. So if only we could come up with an effect that's also a monad and provides this kind of capability of wrapping blocks of code in some sort of local state, then this would work. So is there something like that? Well, for a moment, let's assume there isn't. So let's build our own monad. We'll call it myMagicMonad for context, and it will be implemented by a function from the context. So it might be a common context, like it's really called context in common. Or it might be a map of strings to strings, like in MDC. And FA will be just our implementation. We can define a flat map for this quite easily. We can create a function that takes an instance of this monad and the function that modifies the context and makes sure that when you run the whole thing, you have the original monad, but with this sort of changed context. And then we can have a scope, so basically set the context in this block. So we made a new monad, and it actually sounds like something that we might want to use in this case. But is it really a new monad? It feels too generic and too useful for it to be new. Like, I couldn't come up with this. So here are just a couple of other examples of where you might want to use this monad, this exact same monad. Maybe authentication, so your context would be a user. Maybe a transaction, so your context would be a connection, a database connection. Maybe a trace. Or maybe you have a multi-tenant system and you want to carry the client ID everywhere. Or maybe you're using Zio and your context is your environment. So there's a law by Rob Norris that there's basically nothing new. If it's plausibly useful and sufficiently generic or polymorphic, it's already out there and it's probably already in caps. So did we really come up with a new monad? We didn't. There's already a monad like that. It's called Kleisli, and you may know it as reader T. So why is reader T the perfect fit for this kind of thing? We get automatic passing of context for free, because when you have a flat map node, when you have a sequence of flat maps in a Tacos Final code base, you don't even see the context. It just gets passed down there automatically. And the only place you need to provide the context is when you actually execute the program. So you would provide the root context. And we can also get the current context if we, for some reason, want to. Maybe we are writing an integration and want to save it to MDC or to request headers. then we can still do that with class ask, or maybe we can do this through a type class like applicative ask. It works. And we can change the context in a region of code quite easily with local. But we still need integrations. So everything that we want to be aware of the context of the spans and traces, you will need to wrap it or customize it in a way that it'll see this context and use it. Or maybe it'll set the context. We also need some sort of escape hatches so that the code that was not built with that in mind, for example, some Java libraries or Akka or whatever, you still want to see the transaction or the trace and span IDs in the logs. So you need a way to get from the context that's functional to the impure world and set, for example, the thread local in a given block of code. That's not really hard to implement, and I would argue that it's much easier to do than all the magic that we did to get I/O to work with that, with MDC. MDC was, I wouldn't say MDC is better for context propagation, but it's useful if we can get the context in there. And we need a cool library that provides a nice API on top of classing. So maybe something like this trace thing that I showed you. And Rob also made a library for that. It's not very popular, but I think it's very useful and very nice. So the API is very simple. There are just a couple of things that you need to learn, but you mostly interact with it through this trace type class or trace algebra. And there's an instance that you get for free if your effect is classy with a span. And this span you get from one of the integrations like Jaeger or Zipkind. So basically, this is what our code looks like with Natchez, the library by Rob. So all the trace information that we have here is just creating new traces, and we could still come up with some nice syntax for that to make it easier and to reduce the amount of code here. And as you can see, the client is not aware of that. Like, we are not wrapping the client call in a new trace, because that's what I did in the client itself. I wrapped the existing one with one that takes the headers out of the context, out of the trace. And then we have just a bunch of stuff to create an entry point, which is the thing that creates root spans. And we can use the root span to run this classing to provide the root span that will be propagated to all this execute code. All right, and then we can wrap the client. Am I out of time? Okay, yeah. So just to wrap up, yeah, sorry. So there's some work that we still need to do. Maybe we can use Common to report to get more integrations for free. So I just encourage you to look at the examples, and thank you, and sorry for the extra time. So if you have any questions, just